Today we're going to talk about equations that relate multiple variables to one another, and then we're going to start touching on how you can kind of visualize these sorts of situations. So, equations with multiple variables, which I'm abbreviating here because I don't have a lot of room on the whiteboard. We've talked a lot about equations before, not in the last couple of weeks, but we have talked about this sort of thing when we have a single variable. So when we had an equation involving one variable, for example, to just give you an example that you can think about here, we can say, what if I say 3x minus 2 is equal to 5x plus 6? Well, this is supposed to be some kind of an equation that holds for this variable. And remember, an equation is simply a mathematical sentence that asserts two things are equal to each other. And we call a value for x a solution if it makes the equation true. So give me a second to write this down. Not that this is anything new, we've talked about this before. And how do you find this? Well, the idea is that you kind of just rework this equation by adding or subtracting the same thing on both sides, or multiplying or dividing by the same thing on both sides until you can isolate the x. So in this case, I could try subtracting 3x from both sides, and that would give me negative 2 equals 2x plus 6. Then I could subtract 6 from both sides, and I would get negative 8 is equal to 2x. And then I can divide both sides by 2, and I get negative 4 is equal to x. So the only value of x that is going to make this equation true is going to be when x is equal to negative 4. Now, in a lot of problems in the real world, the thing is, we want to talk about multiple variable quantities. And we will think about some situations where we want to talk about this. In fact, maybe we should start by talking about one of those situations. We've just been talking about computing doses for animals and things like that. And a lot of times you will have a very specific formula for a dose or for how much of something you're supposed to give to some kind of an animal. So you might, for example, find that, let's say that you're looking into feeding a dog or something like this. Well, maybe for dogs up to 50 pounds, the amount of food that you give is going to be something like 2 ounces per pound of body weight. Well, if we let the variable f stand for the food in ounces, and if we let the variable w stand for the body weight in pounds, then we can come up with an equation that relates these two quantities. We can say that the amount of food is always going to be equal to 2 times w, where w is the body weight. So we have this formula here, an equation. It asserts that these two quantities are equal to each other, but it involves two different unknown quantities. And this is not the sort of thing that is restricted to the veterinary or medical fields by any means. You actually have lots of situations where you have different quantities that are related together. Another example where you could relate two different quantities together like this, and where you want to kind of describe it, the situation that is, you want to describe the situation using an equation with multiple variables, might be let's say that we are putting in an order for something, maybe printer cartridges. We're ordering printer cartridges, and it costs $8 per cartridge, and then there is a flat $10 shipping fee. Well, in this case, if we say that M is going to be the amount of money for the order, and C is equal to the number of cartridges, we can figure out how to calculate the money that the order is going to cost us based on the number of cartridges here. And we can say that the amount of money is going to be equal to $8 times the number of cartridges plus an additional $10 for the shipping. Obviously, in this sort of situation, we would want to order as many cartridges as we can at a time in order to get a better deal on the shipping, basically. But this is the relationship that holds between these. And we express this by using an equation. Okay. Now, in general, whenever you have an equation like this, or like the one that we saw a minute ago, that has multiple variables in it like this, in particular, this one has 2 variables, we usually like to think about one of these variables as what is called the independent variable, and one of them as the dependent variable. In this case, the number of cartridges, this would be called the independent variable, and the amount of money would be called the dependent variable. So what is the difference between an independent and a dependent variable? Well, the difference here is going to be that the independent variable is basically the one that, it's kind of, there's 2 different ways you can think about it. One is, this is the thing that we pick. How many cartridges do we want? So in some situations, the independent variable is the one that we can directly control. And then the thing that comes out of it is going to be the dependent variable. In other words, the amount of money we spend depends upon the number of cartridges we buy. In the previous example, when we had the food and the dog's weight, we would consider the weight to be the independent variable. Now, we can't pick a dog's weight. We have a dog, the dog's weight is whatever the dog's weight is. But it's independent in the sense that it's just there in the problem. It's kind of given to us in the problem. And the amount of food that we give, that's what we're trying to figure out. That is the quantity which depends upon the dog's weight. So the dependent variable is whichever variable depends upon the other variable. The independent variable is the one that's either kind of just given to us as this is what this is equal to, and that's that, or it's the one over which we can control and say, okay, this is what we're going to decide to actually do or have in the problem, and then the other variable, the value for the other variable is a result of that. Now, when you have an equation that involves 2 variables, so let's say that we have an equation with, let's say that we have variables x and y. We often use x and y as the variables, and usually x is representing the independent, y the dependent variable when we're just talking about abstract equations in mathematics. Then, just like any other equation that involves a variable, so when we talked about single variable equations, this was an issue too, there are going to be values that make this true and values that make it false. So a solution is a pair of values, and let's just call them A and B, because I want to have something to represent them here. And what we want to say is that when you set x equal to A and y equal to B, the equation becomes true. So let's take a quick look at an example of this sort of thing to kind of illustrate this. Hopefully you guys had this written down. If not, feel free to pause this for a minute and write this down. So if I gave you the equation, let's say 3x minus 2y is equal to 4, well, the pair of values, let me see here for a second. The pair of values 4, 4 is going to be a solution. And, well, why is it going to be a solution? The reason it's going to be a solution is because 3 times 4 minus 2 times 4, well, that's equal to 12 minus 8, which is indeed equal to 4. The pair 1 and, let's see, what would we get here? We would have 3 times 1 minus 2y equals 4, so we would get negative 2y is equal to 1, and so we would get negative 1/2 is a solution, because, okay, so just to check it, we would have 3 times 1 minus 2 times negative 1/2. That's going to be equal to 3 plus 1, which is equal to 4. So these pairs are solutions to this equation. On the other hand, 2, 4 is not a solution. Because if I plugged in 2 for x, I would have 3 times 2. If I plug in 4 for y, I would have minus 2 times 4 here. And that would come out to be 6 minus 8, which is equal to negative 2. That is not equal to 4. So this pair is not a solution. Now, notice here that when we have this when we have an equation like this that has 2 variables instead of 1, we're getting various solutions. When we talked about those linear equations in one variable, one of the things that we said was, hey, you actually only get one solution to these equations. In this case, we're getting multiple solutions. And in fact, I want to make an observation here. So a linear equation in 2 variables is one that can be rewritten in the form ax plus by is equal to c. Now, you'll notice that the previous example that I had was actually written in this form. So here the x and the y are variables, and capital A, capital B, capital C are constants. They're some fixed numbers, okay? The x and the y represent variables, though. And our previous example where we had 3x minus 2y equals 4, well, that was exactly in this form. Now, of course, it doesn't have to start out written in this form. There might be some equation that looks a little bit different, but the idea is a linear equation is one where after we do a little bit of algebra to rewrite it, we get it down into this form. Now, what I claim is that Such an equation has many solutions as long as, well, actually, it's going to have many solutions in general. And here's the reason why. Let me erase this top so I have a bit of room to write. There are a few different possibilities. So one possibility is that capital A is equal to 0. Well, in that case, then this equation just says that by equals c. So y is going to be equal to c over b. Oh yes, this is what I wanted to say. So as long as both A and B are not, or that's not a good way of putting it, is it? As long as one of A and B are not 0. So we need to have one of these two things not be equal to 0, but as long as they are not equal to, as long as they're not both 0, then we get many solutions here. So if capital A is equal to 0, then any pair x comma c over b is a solution for any x. So we actually get, for each choice of variable on x, we get a solution here. If b equals 0, then we can say that this turns into ax equals c. So x is equal to c over capital A. And that means that any pair of the form c over a comma y is a solution. Again, for any choice of y here. And the last possibility is that both of these are non-zero. So if A is not equal to 0 and B is not equal to 0, then what we have is AX plus BY equals C. This can be turned into B times Y equals C minus AX, and that turns into Y equals C minus AX divided by B. So anything of the form x comma c minus ax divided by b is a solution. In other words, any pair of this form is going to make this original equation true for any choice of x. What we're seeing here is that these linear equations in two variables, they actually give you an infinite family of solutions. Now, that sounds complicated in the abstract maybe, but it's actually kind of what you would expect. To make this more concrete, let's go back to thinking about the example I wrote down back at the beginning where we talked about the amount of food that you want to feed a dog. Well, there should be some amount of food that you're supposed to give a dog for any given weight of dog, right? For any weight, there's some amount of food that should be the proper amount to feed that dog. Well, that is exactly what this is saying. It's saying that as long as the food and the weight are related by one of these linear equations, then for any given weight, there's a value for the food that is the right value of food. And that's exactly what you would expect in a situation like that. You don't expect that, oh, there are some dogs whose weight is such that there's no correct amount of food. You would expect that for any given weight, we can figure out the amount of food. And that's exactly what you're getting here. All right, so that was kind of an example of where these linear equations come from. Now, we're going to return to this matter of thinking about linear equations in different ways in a little bit. But before we get to that sort of thing, I want to actually talk about how you can visualize these things, because I think being able to visualize these is really, really helpful. So let's talk now about graphs and the Cartesian coordinate system. Sorry that took me a minute to write down, and I was kind of quiet while I was writing it. So the Cartesian coordinate system, this is actually named after a French mathematician and philosopher named Descartes. Descartes is a very important guy in the history of mathematics. So, for a long time, there were sort of these two branches of mathematics. There was the algebra branch, which dealt with things like equations, like the stuff we were just looking at. And then there was the geometry branch, which dealt with things like figures and shapes and that sort of thing. Now, obviously, people realized that there were relationships here, right? Like the Pythagorean theorem says something about lengths of a triangle, and it does so using an equation. So people understood that, yeah, there are things in geometry that are described by equations, and there are equations that you can kind of think of as describing some shapes. Well, what Descartes was able to do was he introduced this idea. Well, I don't know if he fully introduced it, but you know, a lot of things in mathematics, people kind of built them up over time, and eventually they get named for one of the people who contributed. But the big contribution was this idea that actually everything in geometry can be thought of as, in some sense, described using equations, and every equation turns out to describe some geometric shape. And the way that he did this was by using a coordinate grid system, sort of like what you would see on a map. So if you're reading a map, right, I have some sort of map, and if you look at the legend on or the list of like locations on a map, it'll usually say, okay, this is located at, I don't know, D7 or something. So you go over to where D is along the top of the map, and then you go down to 7, and at the intersection, that's where you find on the map whatever it is you were looking for. Well, Descartes' idea was the following. Take the plane, so the ordinary plane in which you would draw shapes, and put two perpendicular lines in it. And we're going to label these two lines X and Y. And each of these lines we're going to think of as a number line. So the X number line is going to count upwards as we go to the right. So 1, 2, 3 to the right, and then -1, -2, -3 to the left. Now, of course, that's going to go off in both directions forever, but I'm not going to be able to draw much more here. The Y direction, the one that I've labeled with a Y, this one is going to count upwards. So 1, 2, 3 as I go up, and then -1, -2, -3 as I go down. Okay, so two number lines that we place in the plane, and they have to be perpendicular to each other. And now, here is the idea. Any point in the plane can be described by giving how far along the x-axis you need to go and where along the y-axis you need to go. So, if I just mark this point on the plane, I can describe to you exactly where it is by saying, well, look, to get to this point, you have to go along the x-axis until you hit 3, and you have to go along the direction of the y-axis until you hit 1. And the way that we write that succinctly is we write it as a pair 3, 1. So this is the position along the x number line here, and this is the position along the y number line. Now, instead of just calling it the x number line and the y number line, we call this the x-axis. Okay, apparently I can't spell axis today. Axis. And this is the y-axis. So, these are called x and y axis. And by the way, the plural of axis is axes, because we have to be complicated. So instead of saying axes like you might expect, it's actually axes. Don't ask me where this comes from. This is one of those words that I actually have no idea where it came into the English language from. I'm guessing it's probably Latin, but who knows? Anyway, the point is that we call this the x-axis, this is the y-axis, and really, though, an axis is just a number line that's been placed in the plane like this. So it's not just any old number line. It's a special number line that is part of this kind of thing. So what if I were to think about wanting to describe this point? Well, I could say, okay, to go to this point, I need to look along the x-axis. I need to look along this, and I'm along this -1. If I think about, like, where is this in the x direction, it's at -1. And if I think about where is this on the y direction, it's at -2. So this would be the point -1, comma, -2. Now, just to make sure that you guys are following this, take a moment, pause this, and see if you can figure out how you would describe that point. Okay, we're able to figure it out. So this would be at -1 in the x direction, and it would be at +2 in the y direction. So this would be the point -1, comma, +2. Now notice that we can also find points in the plane if we're just given some point and asked to locate it. So if I were to ask you, where is 2, comma, -2, the way that you would figure this out is you would say, okay, this means we go along the x-axis to the point 2, and then we go along the y-axis to the point -2, which is down here, and then the point that is in that position along both of those is down here. So this is the point 2, comma, -2. Again, to make sure that you guys are understanding this, let me ask you guys to pause this a minute and find the point. Let's do, actually, I don't know, let's say 2, comma, 3. So where would you locate this on the plane? Okay, so the place that you would locate this, I would go along x until I get to 2. I would go along y until I get to 3. And this is the point that is 2 along x and 3 along y. So this is my point 2, comma, 3. So why is this so important? Well, the reason it's so important is because using this method, Descartes was able to translate any sort of shape in the plane into a collection of pairs of points. And he was able to take any equation involving x and y and say, actually, that equation can be thought of as representing some shape in the plane. So how was he able to do that? Well, the basic way that he was able to say that equations represent shapes in the plane was as follows. So we go from an equation to a shape in the plane in the following way. We think of all points x, comma, y, whose entries in this pair, in other words, these two values, make the equation true. In other words, he's saying every pair here represents a pair of, every point is represented by a pair of numbers. Take that pair of numbers and plug it into the equation. We just want to consider all those points where the numbers that represent them, which, by the way, those numbers that represent them are called the coordinates of the point. Take all those points whose coordinates make the equation true. In other words, whose coordinates are solutions to the equation. This is called the graph of the equation. So all of the points that make the equation true are going to be the graph of the equation. To give you an example of what this looks like, and we'll talk about this more in the next lecture, but just to give you an example that's maybe sort of straightforward to see what's going on, let's say that I have the equation y equals x. In other words, this just asserts that the two variables have to be equal to one another. Well, if I wanted to graph such an equation, sorry, it takes me a minute to actually make another set of axes here. For any given x value, the y value that I want to choose should be equal to it. So for example, at an x value of 1, the solution to this equation is that y is equal to 1. At an x value of 2, the solution is going to be that y should have a value of 2. When x is equal to 0, y should also be equal to 0. And you can go on and work this out. And in fact, what you see is that for any given value of x, the y value should be equal, which means we are always going to end up on this diagonal line. So all of the points on this diagonal line are solutions to this equation, and the other points are the points that are not solutions to this, or rather, they're points whose coordinates are not solutions to this equation. So we label this shape in the plane with the equation y equals x, whose solutions are exactly this line. And in this way, we have this nice correspondence between equations and shapes in the plane. And this correspondence, by the way, is actually super important in mathematics. This is really the foundation of an entire branch of mathematics called algebraic geometry, which uses the correspondence between equations and shapes in the plane, but also in some other more complicated objects to think about geometry problems. All right, so I'm going to end there for today. We will come back to talking about graphs in the plane, how you can think about them, how you can make them, and in particular, we're going to want to think about those linear equations that I talked about. And in fact, we will see why you call them a linear equation when we do that. But I will talk to you guys in a couple of days.